Welcome. In this and the next two sessions, we'll look at some examples of graphing using calculus and the technique we saw in the previous session. These problems can be quite long because they involve a lot of calculation. To illustrate the basic ideas without getting bogged down in the details, we will first do examples where we have done most of the calculation. Our first example is the graph of the function x cubed minus 3x squared minus 9x plus 11. So cubic polynomials, so the calculations are quite simple, even though they took us a bit of time to do. Back in slide 51, we found the critical values. Those are x equals 3 and x equals negative 1. And to plot the corresponding points, we have to find the y coordinates. So we plug in the critical values, negative 1 and 3 for x into the equation to find the y coordinates. When x is negative 1, y comes out to be 16. So the point is negative 1, 16. I am going to plot that. When x is 3, y comes out to be negative 16. So the corresponding point is 3, negative 16. We will plot that as well. We also found the point of inflection. There is just one. For the point of inflection in slide 65, the point of inflection is 1, 0. We plot that as well. X-intercepts are hard to calculate. They are also irrational, so we won't bother plotting them. The y-intercept is easy to find because it's just the value of y when x is 0. Just to stay with the book's technique, we'll plot that as well, although it's not really necessary. Now, we are going to look at the shape of the pieces connecting these points. That's going to depend upon the sign chart for y prime and y double prime. We did the sign chart for y prime on slide 53. Positive in the intervals negative infinity to negative 1 and 3 to infinity, and negative in the interval negative 1 to 3. And we did the sign chart for the second derivative in slide 63. The second derivative is negative when x is less than 1, positive when x is bigger than 1. Now we need to combine the two sign charts. One method is to simply look at the intervals in which the critical values, the points of inflection, any points of discontinuity, divide the x-axis into. Just mark critical values in the points of inflection. There are no points of discontinuity because we are dealing with a polynomial. They would be at negative 1, 1, and 3. So from negative infinity, I come to negative 1 first. It's the first interval. And then negative 1 to 1, 1 to 3, and 3 to infinity. From negative infinity to negative 1, we know y prime is positive and y double prime is negative. So the graph is increasing and concave down. So we draw a segment with that particular shape. From negative 1 to 1, the graph is decreasing and concave down. 1 gives me a point of inflection. The concavity changes. The graph continues to decrease. It's concave up. The final segment from 3 to infinity, it's increasing and concave up. Note that we have horizontal tangents at negative 1 and 3 because the first derivative is 0. So we must draw the graph so that they seem to have horizontal tangents. This concludes this example, and we will do an example with a discontinuous first derivative next time.